Hello everyone. In today's video, we are going to talk about alkyl halides, and we're going to do two things. We're going to name them briefly, and then we talk about preparation of alkyl halides. So this is done in two ways, basically through radical reactions or through preparation from alcohols. Okay, so in terms of the preparation, within the radical section, we need to talk about stability of radicals. You guys haven't heard this yet. You've had a preview of radical reactions, but there are different types of stabilities of radicals, including allylic radicals. So we'll discuss that. And then in the next video, we talk a little bit more about reactions of alkyl halides. Okay, so first, just an overview of an alkyl halide. Basically, you have a carbon center that's sp3 hybridized, and you have some sort of halogen. Mainly, we're focusing on chlorine, bromine, or iodine. In terms of naming, we've already done this, so I don't want to spend much time on this at all, but basically it's the same type of substituted alkane nomenclature that we learned. And you identify the parent chain and the substituents, and you start numbering where you are closer to the first branch point. So this compound here, the numbering starts 1 on the left, 2, so your two substituents are at the 2 position, and then you just name the substituents in the order alphabetically. So we have 2-bromo, 2-methyl pentane. There are sometimes when we actually have some common names. So instead of having the halogen named before the alkane, for example, this is chloroethane, or more specifically 1-chloroethane, sometimes we switch that and we say ethyl chloride. So sometimes you'll see that methyl iodide or iodomethane. A common solvent that you guys have used in the lab already is dichloromethane here, and sometimes that's called methylene chloride. So in the lab, you guys have seen on the bottles methylene chloride, and that's just a common name that we use. So you'll see that interchangeably, sometimes when I'm speaking, sometimes in your textbook. Okay, let's just take a look at different halogens as we go down the periodic table. What happens is we're increasing the number of electrons, so those are being put in increasingly larger n levels, so the atoms are larger. So when we get from fluorine to chlorine to bromine to iodine, the atomic radius is increasing. The consequence of that is that when you have a bigger atom and you bond it to something, you just have a larger radius, so the bond that you form is longer. So as we go down the periodic table, since the size of the halogens increase, the carbon-halogen bond length will increase as well. This is significant because if you have a longer bond, that's actually a weaker bond. So as we go down the periodic table, we see length increases, but bond strength will decrease. So the consequence of that is a lot of times those bonds are going to be easier to break and can be more reactive. When we actually talk about reactivity of halogens, one other key feature is that when you kick out a halide as the anion, the ones that are lower on the periodic table, those can be better stabilized. So you saw that when we were looking in the acids section, talking about stabilizing conjugate bases. But basically, the larger guys are more polarizable. They can kind of spread out and localize that negative charge better. One of the key features that make alkyl halides really reactive is that you have a net dipole moment. You basically have a carbon that's less electronegative attached to a halogen that's more electronegative. So you have a bond dipole towards the X group, the halogen. So basically that makes your carbon more electrophilic. This is significant because that imparts the reactivity of alkyl halides. That carbon center wants more electron density. It can be reacted with another electrophile, another nucleophile, something more negative, actually a full or partial negative charge, can come in and attack the plus here. So overall, just keep in mind when you see a CH or any C halogen group, you should start thinking of that carbon as electrophilic, and nucleophiles can come in and attack. Okay, I want to just do a brief review of radical reactions. This is something we looked at in chapter 6. These are really important, not just in just organic synthesis, but polymer synthesis, certain biochemical processes. There are 3 main steps: the initiation, the propagation, and the termination. Initiation is shown here, and basically you're generating your radical. So if you have chlorine, for example, you can initiate bond scission here, a homolytic cleavage, where 1 electron remains on each atom. You can initiate that with heat or light. So the main feature of the initiation is just getting this kick-started, generating your radical to start the radical reactions. And the radical reactions that are key is this propagation phase. And basically, propagation is when a radical reacts with a neutral molecule. So for example, the chlorine radical can react with methane. And look what I'm doing. I'm using the fish hook arrows. 1 electron is going, and it's basically in the space between the 2 species, is going in the space, and then another fishhook arrow from the HC bond. This bond has 2 electrons, so one of them is going to go and form a bond with this chlorine. The other is going to remain on the C. So you basically broke this CH bond and formed HCl. And what remains is that methyl radical that you had just formed. That's key because that can then react with a Cl2, a neutral guy, do the same sort of fish hook, forming a bond kind of in the space in between, and this ClCl bond breaks, and you get your first chlorinated alkyl product here. Regenerating this radical is key because it keeps that chain reaction going. Overall, you can do this to form this chloromethane. You can actually keep reacting with each of those hydrogens. So you could get the dichloromethane, the trichloro, and eventually, if you keep letting this go, you could get the tetrachloromethane product. The termination, the final step, is just any 2 radicals reacting together. That forms a bond, and it basically kills the reaction. It terminates it, stops the chain, because you now take out the radical species from the reaction mixture. Okay, so this chapter is key because it really dives in a little bit deeper to talk about what types of radicals you can make. So what if there are different types of hydrogens? In our last example, we had methane. Those are 4 identical hydrogens around that 1 carbon. But look at this substrate, 2-methylpropane. I have 3 methyl groups, so each of these have hydrogens that we would call primary hydrogens because they're only attached to 1 C. This hydrogen, however, and so it's 1 C attached to something else. This hydrogen, however, is attached to a C that's attached to 3 other carbons, so we call that a tertiary hydrogen. So there are 2 types of hydrogens in this substrate. If I carried out this radical reaction, I can replace an H here, that tertiary H, with a chlorine and get this product. Or I could react with any of these primary H's. So I have 9 of them to choose from, so you actually have more, and you could form this type of product. This reaction can keep going. We can form the dichloro, trichloro, tetrachloro products, and so forth. We're going to just focus on what's formed here. If you focus on these guys, what we see is that it's not 50-50, and it shouldn't be, right? Number 1, there are different types of hydrogens, and also there's only 1 of these tertiary guys versus 9 of the primary guys. So what we actually see is 35 of this tertiary chloride versus 65 of the primary product. So what this actually tells us is just by looking at the product distribution, we can learn so much about radical reactions and the stability of radicals. This says that the tertiary is more reactive. So don't let this 35 deceive you. Even though it's a small number, it's still very high given that you have 1 versus 9 primary H's. So this actually says the tertiary is more reactive. The reason why there's less tertiary is just because there are 9 times as many, I should correct that, 9 times as many primary H's to react. Okay, so just based on experimental data, what scientists have observed, they've been able to come up with a range of radical stability. And this is based on the number of alkyl groups. So this will look really similar to what you saw for cationic stability. Basically, the methyl radical is the least stable. The tertiary is the most stable. And so it goes methyl primary, secondary, tertiary. The reason is you basically just have more alkyl groups attached. And alkyl groups, they have electron density. So you have these electron-rich alkyl groups, here specifically methyl groups, that can kind of donate in and stabilize this radical. Because just keep in mind, that radical is in an orbital that's half filled. It normally wants 2 electrons, so it only has 1. So just note that the tertiary radical is more stable. The ones that are more substituted are more stable. This imparts higher reactivity. So if a more stable radical can be formed, basically you're lowering that transition state so that hill to climb is lower, so it'll happen faster. Your activation energy is lower. So here I can just give you an example of the reactivity. Primary is 1, secondary is 3.5. So what that means is a secondary H, something like this, on a carbon attached to 2 other carbons, is 3.5 times faster or more reactive than a primary H, one of these 3. Okay, there's another radical. It's called an allyl radical. And it's a very stable radical. It's even better than a tertiary radical. So just like carbocations, radicals can be stabilized by resonance. A radical is sp2 hybridized. This one here is. So just to be clear, this specific radical is sp2 hybridized. Some are sp. What I want to show here is that this is an allyl radical. The reason why it's allyl is it's on a carbon next to a double bond. This is an allylic position. So this central carbon here has some overlap forming this pi bond here towards the left. This is aligned, these orbitals are aligned with that p orbital of the radical. So what can happen is you can have resonance, you can have that electron delocalization throughout. So you can envision the radical on this left side as well. Just remember, this is really a blend. Resonance structures are a blend or hybrid. So basically you have just kind of radical character on either end of these. So both ends could react. And the key thing here is that an allyl radical is super stable because it is stabilized by resonance. Okay, there is a reagent that can generate allylic radicals. So basically, you can have a reagent called NBS, and it stands for N-bromo-6-cinnamide. Here's your 6-cinnamide part. And if you activate this with light, and here we're just showing carbon tetrachloride as a solvent. That's basically going to be inert and not reactive with this. If we activate this with light, what we can do is generate a radical at the allylic position. So if we have cyclohexene as a substrate, we have 2 allylic positions here and here. That represents 4 different hydrogens. And so this NBS can generate this allylic radical, one of them, say you just use one equivalent of these guys. At the same time, a bromine radical is also generated. So what comes in is reactivity of the Br radical and the allylic radical, say it's generated here, to give you this 3-bromocyclohexene product. These work really well, you get a really good yield. So this is a really nice way to install bromides or other halides into an alkene, and obviously you could do other alkene chemistry with this afterwards, or possibly other alkyl halide chemistry with this afterwards. So just to give you a more expanded scale of the stability of radicals, allylic is the best, then tertiary, secondary, primary, methyl. Vinylic is the worst on this scale. What is vinylic? How is this different? Look at the cyclohexene substrate. You already know next to a double bond, on a carbon next to a double bond, you have the allylic position. This is just straight up alkyl off to the left. But when you're literally on the double bond, that's vinylic, this being like a vinyl group here. So this is the worst because it's on an SP. A radical would end up being SP hybridized. So there's more S character, and that actually works against radicals because radicals actually want more electron density, but more S character means you're closer to the nucleus and it feels more positive. So that's why vinylic radicals are the least stable in this scale. Allylic is better. The other thing that you'll read in your textbook is that this also tracks with bond energies. So allylic has a bond strength that is lower than the others. So that means it's easier to break that bond, essentially, so more reactive. Vinylic is harder to break the bond, has the highest bond energy, so it'll be least reactive. Okay, let's practice what you just learned. So what I want you to do is show all the products formed when the following alkene reacts with NBS. All right, so pause this and then I'll go over it. Okay, so the solution is using NBS. I again kept with the same carbon tetrachloride solvent, activated it with light, which is represented by HNu. What we get out of using NBS again is generation of an allylic radical here or here. These are identical, here or here. Again, you generate this bromine radical that can then react with that allylic radical, forming the bromide. So one product could be reaction here on the right side. Another product could be reaction here on the left side. So both of these can be formed. Yes, there's a possibility if you do add a lot more NBS, you can start getting dibromo products as well. But just at first glance, just reacting once, you have a probability of reacting at either of these. And I'm sorry, something that I need to clarify is you get both of these, and I apologize, it's not this product. Both of those give this product. So you can react here or here with equal probability to give this type of product, because imagine if you flip it over, it's the same thing. The other thing that the other product is not formed until you realize once you generate an allylic radical, you can have the resonance to give the radical on this side. So let me just go over that again. The obvious reactions are here and here on the next to the double bond to give this product. Then now envision a radical here. So let me just show that here. So you can have a radical here, and then you can form with a fishhook arrow your double bond here now, and then your radical stays here. So you have a radical at this position. And that then is going to give rise to this product here on the right, where the double bond has shifted because now you've looked at the other resonance structure, and then the bromine is going to react at the center here where a radical forms on this side. Okay, the last part of this video is forming alkyl halides from alcohols. This is a really nice, straightforward way to make alkyl halides. This works really good with tertiary alcohols. We'll get into more details later. But basically, you could start with an alcohol. And hydroxy is not a great leaving group. So you kind of want to soup up this leaving group. The way that you do that is protonate it and turn it into water, or OH2 plus if it's attached here. So you add an acid, and why not add an acid where you generate an anion, that's your halide, and the halide can come in, attack the carbon, and kick out the hydroxide. Sometimes though, and we'll get into this in more detail, the water leaves on its own, giving a carbocation, and the halide can come in and attack. So the acids that are typically used are HCl, HBr HI. Again, with the tertiary alcohols, this reacts really rapidly just because you can form a tertiary cation. So in that case, that water does like to leave first. If you're looking at secondary or primary alcohols, those don't work as well with this method here using the acid. So there are two other reagents that are typically employed. If you want to generate chlorines, you will generate, you will utilize what's called thionyl chloride, this SOCl2 reagent in the presence of pyridine. And this alcohol attacks the sulfur. You create a really good leaving group, and chlorine comes in and kicks out. So basically, you swap out the OH for a Cl using this reagent mixture here. The pyridine is there to sop up any HCl liberated in that reaction. So again, secondary or primary, if you want to make an alkyl chloride, use SOCl2 and pyridine. If you want to make an alkyl bromide from a secondary or primary alcohol, use PBr3. So PBr3 can react in a way kind of similar where alcohol attacks the phosphorus, a bromine can come in. But overall, just know that your alcohol is replaced with a bromine to give the alkyl bromide product. Okay. So we are going to end with just practicing here what you just learned. How would you prepare the following from alcohol precursors? So make this from basically the corresponding alcohol, and then make this from the corresponding alcohol. So pause, write out a full reaction with the reagents, and then unpause and I'll go over it. Okay, for the bromocyclohexane, that's this compound here. If you come from the corresponding alcohol, you can see that's a secondary alcohol. So you won't use that HBr ether method. You would use PBr3. So PBr3 and ether is going to generate your alkyl bromide from the corresponding alcohol. For the other compound, that is a tertiary alcohol. So then you could just use the HCl if you're trying to generate the chloride. That ends up protonating here, making water a very good leaving group. And then you could swap out water for this chlorine and get your desired alkyl chloride product. Okay, that's where I'm going to end today. And then in the next video, we'll talk more about reactions of alkyl halides and what you can do with them.